Suppose two waves from some coherent sources are coming and meeting at a certain position x at some point t in time. Then the resultant will depend on either their phase difference or the path difference basically between the two. So the difference can be expressed in either units of the phase angle theta or the wavelength lambda. Let us look into this in more detail. Constructive interference. When the phase difference between the two waves are an integer multiple of 2 pi, then constructive interference happens. That is, the two waves meet up and they produce a larger wave. They interfere in phase basically. So the condition is that the phase difference between the two waves. Remember, phase is the argument of the sine wave or the cosine wave. And if this phase if the phase differs by n2 pi between the two waves, then basically we have constructive interference. And in this case, n can assume any integer value including 0 and any positive integer value basically. You can also think of this interference in terms of path difference. So if two waves differ by m lambda, m is an integer that starts from 0 and goes to positive values, 0, 1, 2, 3 for example. So if the two waves differ by m times lambda, lambda being the wave function, the wavelength, then the waves also interfere constructively. N and m are called orders basically here. So m equals to 2 means second order. This figure again revisits constructive interference. So the two waves coming in are in phase. That is, they have a phase difference of n2 pi. N could be 0 or 1, 2, 3 or any other integer, positive integers. And the resultant wave is much larger, has maximum amplitude basically. And what about destructive interference? So when the phase difference between the two waves are n pi, and in this case n is an odd integer starting from 1, then the waves will interfere destructively. Similarly, we can again think of this in terms of the path difference between the two wavefronts. If there is a path difference of m plus half lambda, lambda being the wave function, then again the waves will interfere destructively. The half wavelength basically gives the out of phase, 180 degrees out of phase component at the same location. So m here starts at 0 and can assume any integer, any positive integer 1, 2, 3. So the condition is that the two waves have to differ by a path length of m plus half times lambda. Lambda is the wave function, wave length in this case. And this figure again revisits destructive interference. Here the phase difference is basically n pi, n being an odd integer, and then we see that the waves are completely out of phase and they annihilate each other. The resultant has minimum amplitude. Now let us discuss light waves. You have all heard about lasers. Lasers are a source of light waves. Lasers produce a single wavelength light wave. The waves are all in phase and they are all coherent. One of the applications of a laser is to write and read information from our storage devices such as CD, DVD or Blu-ray. In each of these technologies, different wavelength is used. As technology has developed, these things like the lambda that is required to read and write has also changed. In this case, we see that lambda is quite small for a Blu-ray compared to a DVD. This is an interesting experiment in physics where you have two openings or called slits, double slit experiment, and there is a light wave that is falling on this surface, and the light waves trace out circular wavefronts as they go through the slits, and these two waves basically create some interference pattern on the screen that is located on the far right side. These arrows are showing a slice basically through the wavefront and showing the direction of propagation of the waves. So, and this shows two waves from the two slits interfering at the central position. And if the two waves are in phase are coherent and in phase, and their path difference in this case at the center is 0 actually, the phase difference is also 0. And if you go to the higher modes basically with m equal to 1, so in this other position, say S2 minus S1 is equal to lambda, just one wavelength apart, then we can have even higher m's, higher orders. S2 minus S1 for the next location on the screen is twice lambda. This is order 2. And then in between these m's, you can have the destructive interference cases, m plus half lambda, where S2 minus S1, the path difference between S2 and S1 is actually half lambda in this case. This is the 0th order, m equals 1 for destructive interference. And if we do an interference plot, then we get an intensity plot on the screen as shown here, where there is peak intensity at each of the m's. When m equal to 0, the intensity is the highest, and then for the higher orders, the intensity diminishes, but still we can see bright spots basically. And in between these m's, notice that the intensity drops to 0 basically. So these are the locations where destructive interference takes place. That is, the path difference is multiple of lambda over 2 basically, as is an odd multiple of lambda over 2. And in reality, like if we do the experiment, we will observe a pattern like this. You have higher intensities at the m values, and very low intensity, the dark spots in between these bright spots. And let us revisit the path difference. So this shows two light rays from the two slits, and the slits are separated by a distance d. So let us calculate the path difference. So if we know the angle, so the two light rays are basically almost parallel. So we can draw a perpendicular line from one of the slits to the other ray. This makes a 90-degree angle with the propagation of the ray, the direction of propagation. And we have this angle theta between the surface of the slit. And then, so the path difference is given by d sine theta. D sine theta, the path difference between the two light rays. And so if this path difference is a multiple of lambda, m being an integer, so d sine theta equals m lambda, this is the condition for constructive interference. And for destructive interference, if this path difference d sine theta is a multiple of m plus half, basically the lambda, then we have destructive interference. M here is any integer starting from 0. So another condition here is that the sources must be coherent. Otherwise, it will be hard to observe these effects. So can we obtain an expression for the position of the interference fringes, the places where the bright spots occur or the dark spots occur? This also we can obtain from the geometry of the system. So the slits are separated by the small d, and let us assume that the big screen on the far right is separated by big D. And then theta is the angle from the horizontal, from the center of the slit to the screen at a position y. We want to know the intensity pattern at y. And so we can use this geometry to analyze the problem. And we have to assume in this case the big D is much greater than the small d, which is a realistic condition in the experiment. The slits are very closely spaced and the screen is placed quite far away. So we have to, let us make the small angle approximation in this case, because big D, capital D is much greater than small d, we can write sine theta equals tan theta, and this is actually equal to theta, and then sine theta is given by y over capital D. So then we know the interference condition for a bright spot. For example, for a bright spot, d sine theta has to be equal to m lambda, where m is an integer. And then we can write sine theta, if we divide by d on both sides, we have sine theta equals m lambda over d. But we know that sine theta is also given by y over capital D from the last slide. Now we equate the two, m lambda over small d equals y over big D, capital D, and then y is given by m lambda capital D over small d. So this will give us, for each value of m, this will give us the position of the bright fringe, basically, the bright spot. Now let us look at the phenomena of diffraction. Suppose there are incident wave fronts that fall on a screen, and there is a slit on the screen, and so under some circumstances these waves that are kind of plane, the incident waves are kind of plane, they will curve or bend basically as they pass through the slit. So this is called diffraction. Outgoing waves are called diffracted waves. Diffraction is more visible if the opening or the width of the slit is comparable to the wavelength of the light incident on the slit. If the slit width is several times the wavelength, then the light waves will bend by a very small amount, as shown in the first figure on the left. If you reduce the width of the slit and it becomes comparable to lambda, in this case 3 lambda, then you see the wavefronts of the light wave will bend more, curve more. And then if the wavelength approaches the slit width lambda, then the curvature will increase even more. They will become almost circular waves as they emerge out of the slit. So diffraction is basically the bending or spreading of waves through a narrow hole. The amount of diffraction occurs depends on the size of the opening compared to the wavelength. So it's the relative width. It is the length scale, basically, the width versus the wavelength of the incident light, that determines how much diffraction will take place, as you have already seen. So for the two slit experiment we have shown, so we will observe the fringes when the slit width is approximately equal to the wavelength of the incident light, because we need diffraction to occur in that case. And so here we show some diffraction pattern from a circular aperture. You can see consecutive rings of circles. So these are also the bright spots, the higher M's, basically, the orders. And you can see diffraction from a square aperture, interference patterns.